Awesome. So, okay, cool. This is session 4 of Fault Tolerant Friends. We're going over the Back to the Basics broadcast. So let me share my screen again. So we had, I had put these kind of a bit randomly before I had actually understood the subject. So I had put this as a reading material, as well as Christian Cachin's kind of EPFL notes here, which I think are good, but I think, I guess in a sense, I find them academic, and I think the academic way, at least what I found, is very kind of, let's start with the minimal assumptions and then construct our theory. And I think the thing that could have been better here is that most people in the room, or most people who have worked in blockchains, kind of already assume, oh, I know what asymmetric cryptography is, I know what a PKI is, I know what, kind of a trusted setup is. And I think if you assume that, you can have much simpler, kind of consistent and reliable broadcasts. So I think that's the approach that I want to take. So I will start instead with this post that I wrote last night. So I'll go through this a bit for maybe 10 minutes, 15 minutes, and then you can stop me anytime, and we can kind of just discuss whatever. So I'll try to not like read through this too much, but the main idea, I think, for why I'm interested in this is, I don't know if anyone has seen this picture, but this is shown in a lot of like the classical literature, where you start with your reliable channels, which just means you have point-to-point channels between all of your nodes, which typically just means you have symmetric crypto between them, so they can authenticate messages coming from that channel. But that's it. So no PKI, which we'll see. We will add the PKI, but then on top of this, you kind of have a reliable broadcast or consistent broadcast property primitive here, and then a binary consensus. You put those together, and that's kind of where you go to. Here they construct it very academically, but atomic broadcast, also sometimes called total order broadcast. In blockchain, people just call this consensus, right? When we say consensus, we're talking about this because it's kind of we're just trying to have a replicated log that's growing, where client can submit requests and they get appended to this log and pass through the state machine. So that's also why it's sometimes called state machine replication. Right, so there's a lot of basically lingo, and even as I was reading through the asynchrony and the decentralized blog posts, I often get like very confused. So one of the first thing here is that if you go to the, so I think this post is right. So this is one of the main posts. So actually, if you, so if you go here and start here, and you go consensus agreement and broadcast, right? So this is kind of the basics. So decentralized thoughts will start you with this, with the agreement problem, with the 3 properties, and then the broadcast problem. But then it's a bit confusing because you go back, and then you see, when you continue, what he calls here broadcast, you see that there's a termination guarantee, that if you're reading from Cachin's note, this is actually a very strong termination guarantee. And this termination guarantee is what? It's actually that every node must every honest node must terminate. And in this case, you're actually in consensus territory, where the FLP impossibility will hit you, right? So all that to say that I was very confused by this, and that's why I think it would have been better in the post I just mentioned if they named it terminating broadcast. So we can get back to this, but what I've been saying is basically this diagram. Right, so the main thing with broadcast is that you can show what the post that I just showed does is basically you can reduce broadcast to consensus. Difference between them being that consensus is kind of a multi-writer concurrent object, whereas broadcast is we start with a single leader. But you can show that you can reduce them one to the other, right? And that's what the blog post is doing. And this is why when you're in async network conditions, then FLP impossibility hits you, and you need either kind of a randomization so you won't basically have deterministic termination. You'll have termination with probability 1, or otherwise you need to do the classic thing, which is come back to partial synchrony, and then you can finish. That's the idea. And then all of why do people then call. Right, so why, if we go back to this diagram, do people talk about the reliable broadcast as being kind of a separate thing from consensus? right? Because if you go to these nodes, then they're actually kind of shown as being the same thing. And the point is that the broadcast primitives that people use inside these like SMR kind of algorithms are weaker liveness guarantees. So they're these guys down here, right? So you remove the termination condition. You don't ask for that. You ask for something weaker. And in this case, so you get something that's kind of easy, fast. You just do this, and only at the end you kind of, okay, boom, like all of my, let's say, writers have broadcast their messages. Now we can run a consensus algorithm to kind of agree. So I'll go through this in more detail, but so the post, going back to this guy here that I was following. So if you look at these carefully, you'll notice that the agreement is exactly the same, and the termination property is also exactly the same. Right. So the only difference between these two guys in this model is the validity condition. Right. And then what's the main difference is just like the broadcast, what you ask for a broadcast kind of implementation to be successful, to be valid, is only if the leader is honest, then we decide on V. Whereas in the agreement cases, if all of the nodes, because all of the nodes are proposing something at the beginning of agreement, there's no like kind of designated leader. So only if all the nodes have the same input, then we must all decide on V. So that's basically what this section is doing, right? It's just breaking it down, saying that, okay, they have the same condition, and then only the validity, which is a safety property, is slightly different. But the whole point of the blog post is that it's not significantly different. We can always kind of take one, and if you have a solution to one, you have a solution to the other guy. And that's why we kind of can come to the conclusion that terminating broadcast is equivalent to binary consensus, and they both get hit by FLP. So if we want some like a simpler primitive, basically what we'll do is you look at the actual liveness, so the termination property. So you look at this guy. It says all nodes must eventually decide on a value V and terminate. This is the thing that asks when you want everyone in a deterministic protocol to terminate and propose a value, and well, commit to a value, sorry. This is the thing that is strong. And in order to break this kind of this wall, you need to, there's two ways, right? Either you get out of asynchrony. So you go to partial synchrony or synchrony. Or you add randomness. In this case, you can beat. Or what these weaker primitives are doing is just, okay, I will ask for my protocol. I will ask less of my protocol. So we always maintain the same safety. So we always, right, very important, we always have the agreement property. We don't ever want two honest nodes to be outputting a different value. This is very important. And all of the different broadcasts that we will always go through, they always have this property, right? Obviously, otherwise, I mean, it's just not a useful broadcast. But what we can do is we can ask less of the liveness property, and this is what we'll do. And if you go through the Cachin the Christian Cachin's notes, they're basically just walking through the consistent broadcast and the reliable broadcast and showing implementation for those. Right, and so basically, once I realized this, I just very succinctly was able to compress Cachin's notes into my brain into what is all of this doing is showing different implementations for these broadcasts. So as we saw, the terminating broadcast is the strongest category, which he talks at the very end, and he just calls it consensus, which is also confusing because he never calls it like a terminating broadcast in the same way that the decentralized thought does. But this is, you're always asking your nodes. Every node must terminate. The simplest one, actually, so if we kind of reverse and we start with where the nodes go, all that you ask is, oh, if there's an honest leader, then everyone must output the correct value. So that's the only kind of liveness requirement that you have, right? So these are always kind of conditional liveness properties. If we start with an honest leader, he will send the same value to everyone. We will all finish. Of course, we always have consistency. So the consistent property, the agreement, which says if we don't have an honest leader, in that case, we don't need to terminate. Like we don't require any node to terminate. So if you go to the reliable broadcast, if you ask a little bit more of your broadcast, you just ask, okay, now I want not only if the leader is honest, but also if any one node manages to terminate, right? So if somehow it manages to receive, its certs, then I want everyone else to terminate. That's what reliable broadcast means. So that's kind of it's still a conditional, and it's like as good as you can get to kind of everyone terminating, but it doesn't guarantee that everyone will terminate. It just guarantees that if any one node terminates, then we all terminate. If any one node is able to commit, we all commit. But there is still a scenario where, if the leader, basically what happens when you have a single leader is the leader can just decide, okay, I'm not doing anything, right? Let's say it just crashes. If it crashes, you cannot guarantee termination in the single writer model. And that's why you kind of need to go to a consensus model or a multi-proposer model. And then kind of FLP hits you in the face, right? So that's always kind of the thing. Okay, so with this in place, I think we can, if you guys have read through the Brock posts, we can go through this after. But one thing that really surprised me and is that there's this other great article, which is the key principles underlying partial synchrony. Basically, right at this point in time, as far as I understand, Tobias, correct me if I'm wrong, but basically every single blockchain out there is basically in a partially synchronous model, other than like Bitcoin, which is in a synchronous case. But I think the few protocols that were kind of asynchronous are kind of just being replaced. So one example, Sui started with their the Aptos, or anyways, all you need is DAG stuff started with the asynchronous model, but they've kind of moving back to partial synchrony. All that to say that here he breaks down what do you do in the partial synchronous case. And he says, okay, you start with a reliable broadcast. And then he basically says, oh, well, yes, that's good, but you won't get, you will not get liveness. And then his attempt to is you modify it basically to be able to change the leader. So that's where you need to do your view change. So I think we should probably kind of go through this in a separate meeting. I think it's like super important. That's kind of the big mental step between broadcast and then going to consensus. But I do want this session to remain on broadcast. But my entire point here was that when I read this over the weekend, and then I realized, wait a second. So, okay, we have this protocol for reliable broadcast. They're saying this also runs in 2 rounds. It's super simple. What have I been doing? So if you compare it to the Braca that we read, this guy is like much more complex. There's 3 rounds. So what's going on? And I was very confused for a while until I realized that the protocol only needs authenticated channels, right? So again, this is what I was saying in the beginning, that these kind of more academic approaches start with, okay, we want minimal assumptions. We don't want to assume asymmetric crypto. And then they come up with these like constructions, but actually there are much simpler constructions when you do assume asymmetric crypto, and a broadcast like trusted setup phase where we just exchange our public keys. And what you get this much simpler looking thing. So basically coming back to this is what I have here. So all of Cashin's notes, which took me like, I don't know, many hours to read, have in the end been compressed in my brain kind of down to this, right? So if you assume you have asymmetric crypto, the solutions for consistent broadcast and reliable broadcast are super trivial, and it's basically this algorithm. And this is an algorithm for consistent broadcast. It's literally just like a quorum intersection, right? So the quorum intersection just makes sure that there's no, basically you only commit once you've received 1 quorum, n minus T parties, n minus F parties. And this will make sure that there's no, what is it called? Anyways, that basically, it makes sure that no 2 honest parties can commit to the different values. And then if you want to get a reliable broadcast, which means if any one node commits, the other nodes commit, you just uncomment this line. And it is before you commit, you just, whenever you receive a cert, you just forward it to all the other parties, right? that's basically the argument that I think I've also seen. I mean, we've talked in the previous sessions, but there's always kind of this P2P assumption where, okay, I get a cert, I just forward it. And I think Solana or the Alpenglow makes this similar kind of assumption. But it's like, if I commit, boom, I'm sending it on network, everyone else is going to commit with me. And this is basically what reliable broadcast is, right? The reason why you can't do this in Braca and why Braca needs a third round is because in Braca you don't have certs because you don't have asymmetric crypto. So I basically I cannot prove to someone else that 2/3 of the validators did sign a message because all I have is a symmetric crypto, a symmetric signature from them. So I can't use that to prove to anyone else. But okay, does this make sense? This is like, this is basically the basics. I think this is like if you need to remember one thing is like this piece of code. So, yes.
So can we understand like basically the consistent broadcast and reliable broadcast? Like as you said, the only difference is one line of this forwarding this pre-commit message, and by using consistent broadcast, it's basically, can you understand? I save us one round in a sense, or it's not like it's like does forwarding count as one round, or it doesn't count?
Okay, so I'm really happy you're asking this. I basically asked the same question to Kartik on Twitter, and so basically in the thing that happens is that it's still like the theoretical model versus practice, right? So in practice, I guess what you're thinking is the same as me is, yeah, when I see this and I'm going to implement this, what's the assumption I'm making, right? Is this going to be blocking? So am I actually waiting for an extra round trip before I commit or not? And then okay, what is TLS giving me? Wait, a TLS session could actually break, so therefore I have no guarantee, right? You need to think through all of these things. But what the theoretical model of these things does, right? You're always even if you're in asynchrony, right? All of these different models always assume that you have perfect channels. So they eventually deliver all messages. They don't drop any messages, right? So all of this is always done kind of asynchronous. And they just have the model, oh, this is not like, basically they will tell you, oh, this is not a third round because I'm just like I could even move it after the commit, right? Or I guess maybe that's not true because then you would crash. But so you need to make sure you put it on the wire and then you can commit. And I know that eventually people will receive it, even in the asynchronous model, right? Which is like a huge assumption. It's definitely not true in practice. So I would actually be curious for people who actually implement this, like if for example, like Patrick O'Grady was here or whatnot, I'd be curious for it, right? Because, well, okay, first, does this answer your question?
Yeah, so for my understanding, it's basically you saying like the theory model, they're different, and for the reliable broadcast base, like we have a strong assumption that we believe this message will be eventually delivered. You are also curious about in implementation how much this is gonna be a difference, because it's like a constant number of difference in the number of rounds, like from 2 rounds to 3 rounds. And I will also be curious, like in real implementation, what's the real difference gonna be? Because it's pretty niche, like a
right. So,
like a very tiny spot in the theory, a subtle point.
That's the thing, right? So in the theoretical model, you can basically you don't have to block on this call because if you put the message on the wire, it's going to get eventually going to reach the other validator. So that's fine. In practice, right? And when you actually ever implement code, you're actually going to want, if you want certainty, like you need to block on that call. And the way to be reliable is literally you just like keep sending the message until you get an ACK from the person, right? That is basically what TCP is doing. But the problem is you can't trust TCP in the real world because the TCP connection could also break. So you need to actually at the app level block on this call, and then you're adding a lot of latency, right? So
yeah, that's why it makes me really confused. Like you previously mentioned, like we have lots of assumption that we have this asymmetric assumption, the PK assumption that could make the broadcast much easier. And in real world, like all the connection through TLS, TCP, and with those infrastructures, I don't know, like why that cannot be like a very practical assumption, we just use that? And what's the use case of we have like a much smaller assumption, but it doesn't really helpful in the real practice?
Right. Okay. So I mean, I guess what I'll say is this is just kind of the compressed theoretical model, right? So it's more. I think this is the thing you should have in your brain, which is the simplest way you can remember the difference between these models. Now, it doesn't mean in practice this is actually what you implement, and I don't think anyone implements this in practice. That being said, there is something interesting that I know. So last time when we had Kartik, we went through his pipes model. I don't know if you were there. So there is a place where he says, I don't know if I'll be able to find it. Oh, I think it's in the core there. Yeah, right here. Okay. So in this section at the bottom, so in this model, basically they're kind of analyzing, right, the different, they have a predictive model for the throughput kind of bottleneck that you'll hit. It doesn't matter so much if you don't understand the model, but the point is here, what he's saying here, which really like found very memorable, is that their model predicts that in the single center case, blah, 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 then the corresponding term is O of n, blah, blah, blah. But okay, here, perhaps to avoid these issues, practical instantiation of DAG-based protocols tend to use a form of consistent broadcast rather than reliable broadcast for the purpose of block propagation. Right, so I think this is precisely what happens in practice. It's your reliable broadcast is cheap theoretically, but in practice it's not, because you need to block. So what people do instead is they just always kind of go back to the consistent broadcast when they implement things in practice. And then to get the reliability, you actually get that from your consensus protocol on top. So your consensus protocol is the place where you're actually going to make sure that everyone is able to kind of deliver. But of course, it also means that you're not kind of walking in lockstep and waiting for everyone to have reach, to have gotten their cert, right? So we're trying to go like optimistic responsiveness, trying to go at the network speed, is always saying like, I'm not going to be reliable and make sure that everyone, all the validators have gotten their cert. I just need, as long as I know that like 2/3 of the network, we have our certs, we keep going.
Let's see.
I actually have a comment about this, because so like all of these notions of broadcast, even the weakest one, as you rightfully pointed out, they all still assume that the network is able to deliver all of those messages eventually, right? So if I'm sending a value, everyone, all the honest nodes will eventually receive it. And this is like actually quite a strong assumption on the networking layer, right? So what happens in practice is, packets get dropped, and then you can use TCP, but what could also happen is that your computer crashes, and then you have to reboot, and you lose all your TCP state. So you need to really, if you want to guarantee that every message gets delivered, you need to implement this at the application layer, a retransmission mechanism. And then what is sort of practically a problem in blockchains is that the number of messages, I mean, you're not doing one-shot consensus, you're doing continuously consensus. Consensus produces new artifacts at some rate that may be unbounded, right? So it could be that consensus progresses super quickly, produces new artifacts. Now you're the networking layer, you have to push out all of these messages, and you have to make sure that every message gets received by every validator, essentially, right? So what do? You keep track of all the messages, you get receipts for the ones that have been received, but now you're kind of running into the problem that consensus produces at an arbitrary rate these messages. Your networking layer is limited by real-world bandwidth constraints. So you can, in principle, you can run out of memory, right? You will, if your networking layer is slower than consensus, you run out of memory and you crash, right? Which is bad. The other option is that you can slow down consensus. You can tell consensus, hey, my networking layer is not able to keep up with the rate at which you're producing artifacts. But this is actually not a very attractive option, because it could be that only one of your peers is very slow. So it could be that you're sending all the artifacts successfully to everyone except for one peer, and now this one peer is slowing down consensus. So that's also undesirable. And then the third option is that you simply drop messages at some point, but then you're actually breaking the guarantees that all of your liveness proofs in your paper and your favorite consensus protocol reliable, right? So you have this trilemma between these three bad options. And so this is we had a paper about this problem and how to mitigate this using a new weaker primitive that we call abortable broadcast. So essentially, the idea is that while consensus can produce an unbounded number of artifacts, the typically consensus protocols only consider a bounded number of messages relevant at any given point in time. So you can say, if you have like a really old message, you don't actually need to deliver it anymore to all the peers. Okay, it becomes irrelevant. And so in this abortable broadcast primitive, we make that explicit. So consensus says, please broadcast this message, but it can also say, okay, this message is no longer relevant. And then because the number of relevant messages at any given point in time is bounded, the memory consumption on the networking layer is also bounded. And so that's how we break this trilemma. But I think this is kind of understudied because, people love to write consensus papers in which they assume that the network can do magic, but yeah, it cannot. So I will link that paper in the chat.
Please, yes, awesome. That's really
So just curious, like Tobias, for your first point, so is it saying that basically we are using this synchronous assumption plus this what is that? Plus this like a cross or byzantine assumption to basically to model the real world case that the network delivery may be bounded by some time, or if it's out of that, the packets may be lost. Are we using both of those two models to model the real world case?
Well, I'm saying that like asynchrony, which is sort of the weakest, the model that makes the weakest assumption about the network, right? Even that one makes too strong of an assumption. It makes the assumption that we can deliver all messages eventually, and that's too strong of an assumption in reality.
Okay.
I'm not sure if that answers your question.
Yeah, I'm just thinking about like how do we really reflect the synchronous assumption in the real world case? Because I like Sam Priest mentioned like most of the practical blockchains we're using either synchrony or partial synchrony, and I always have this confusion why we even discuss about this asynchrony case in discussing all those like broadcast or consensus models, because I think it's pretty like impractical, or basically like why are we having this model? So that brings me like how do we connect the real world case? What is this synchrony assumption modeling the real world case? Is it like related to network settings? Is it related to some other settings? So yeah, that's basically my question.
So your question is, why do we care about the asynchronous?
Yeah. And I think like you mentioned, like you maybe want to discuss this in a separate session, but I think it's still worth a little bit discussion here because like for your previous discussion for the first 2 or 3 sections of your writings, I assume that all those analyses are worked both in the synchronous setting and asynchronous setting. You split out this terminating broadcast because this termination property may not be working for broadcast under asynchronous setting. So that there is some like hidden assumption inside that. So I think it's still worthwhile to bring this up to say there is a separation here.
Yeah, for sure. I think we can go back. I actually have a section like down below that we can actually touch on these. Yeah, that being said, I think, well, the progression is more, I think, you can start with synchronous assumptions, and then in the synchronous setting, like synchronous assumption on networking is super strong, right? It means there's never going to have any blip. There's never going to have any DDoS. Like there's always a known kind of delay on all of your links. I think that's a nice starting point, but the problem there is if you make any kind of, you can make some pretty strong protocols. Like for example, the Actually, something I didn't even touch on is the Dolev strong broadcast, which is a separate like synchronous broadcast where you can actually tolerate all the nodes being Byzantine except for 2, and then you can kind of still you can still terminate. But the problem there is that if your synchronous assumption is actually not true ever, then you lose safety, right? Which is typically really bad. So typically what we want to say is like, okay, so I don't want to have this, so what do I do? Then the historical progression is just like that's too strong of an assumption. So let's go to asynchronous model, which is just like, it's your classical eventual, like the reason why people have this is because the whole kind of 2000 era, even 1990s, was just like, oh, let's go to eventually consistent, eventual delivery, right? It's just an easy model, which is kind of in TLA plus, you just have your modal operators like eventually happens, right? That's kind of why it comes about, is because it's a nice theoretical construct. It's easy to make logical deductions from it. And I, at least that's my current understanding of why you'd want something like that. But then the problem is like, okay, in this model, well, then we get the FLP, which to be honest is not even that big of a deal, because anyways we can solve it with randomization. But and partial synchrony is just, okay, how do I want to still make kind of synchronous assumptions for liveness, but not for safety, right? That's kind of where the partial synchronous model is coming in between. So it's like I have all of my broadcasts, all of my consensus, everything is always going to be consistent. So there's never going to be, regardless of what the networking is doing, I'm always going to be safe. But I will only get liveness once the kind of blips or the DDoS or whatever the networking is back to a synchronous state, which is this GST time in the middle. So I think that's kind of the natural progression. Now, what Tobias is saying is like, even this, like, it's weird, right? Because your asynchronous model, in a sense, is like super weak. But in some senses, it's also too strong, right? That's kind of what he's getting at. So it's, and that's kind of, I think, well, I don't know. I'm actually curious, Tobias, in this paper, if you, like if it's easy, and I don't know what exactly you guys are proposing, but if it's easy to kind of have theoretical kind of proofs with once you go past the asynchronous model.
Right. I mean, the observation is just that I think this asynchronous model, is seen as being like making very weak assumptions about the network, even though it actually has, in some ways, a very strong assumption. But then in practice, we can replace this with a different, with a different primitive, I would say. So rather than saying, okay, we're going to broadcast and we're going to guarantee that every single message eventually gets delivered, we say every single message either gets delivered or it gets aborted. And so aborted means that the consensus protocol says, okay, this message is no longer relevant, so you can ignore it. And in practice in blockchains, you can achieve this because you have, at regular intervals, you have checkpointing. So all the messages prior to that checkpoint are kind of become irrelevant. You have a checkpoint message that summarizes the entire execution state and the consensus, whatever. And this is all you need to catch up, right? So all prior messages become irrelevant. You have this checkpoint message, and then you have the messages since then, but they're bounded in length because you have regular checkpoints. So in practice, most consensus protocols only have this sort of bounded number of relevant messages at any given time. And the guarantee then becomes is that each message either gets delivered or it gets explicitly declared not relevant anymore. And I think that's sort of a better compromise between, what consensus should provide versus what networking can be guaranteed to provide.
Nice, that makes sense. Yeah. Also, please share in the Telegram. I think so we can. I'll definitely want to take a look at this later. Anyone else has questions for Tobias or anything we just discussed? I think something interesting that this really reminds me of is when we had Victor Shoop, we discussed simplex, and whenever you have these consensus models, which are also kind of doing some form of pipelining or just parallelizing kind of the steps, and simplex is very explicit, and I can change basically as soon as I get a you know, the first vote, I kind of jump out to the second. Well, as soon as I get either a timeout, right, or that I get the first serve, I kind of jump to the next view, and then the finalization of every view kind of happens in parallel, right? So the question is just like, oh yeah, if you go through time. So to summarize, I guess the thing that I found interesting in your comment is that I've always thought basically of this notion of broadcasting happens first, right? And then we do consensus on the graph. So that's also the DAG kind of approach, where we just let the network run at network speed, and then we kind of in time, you know, after sometimes we'll do these cuts on the DAG, or also what Autobahn is doing. So consensus I've always thought of as trailing. So the network is leading, and then when you have these blips, you just don't get finalization for a while, but then boom, later we come and we actually get consensus finalization on some values. But what you're saying is you can kind of also have I mean, yeah, I guess what you're saying is kind of consensus trailing the network is kind of a weird, because basically you always will only reach consensus on stuff that is in the network. But I guess what you're saying is if you just keep going for a while and you kind of never reach consensus, then you have the network kind of doing work in parallel for all of these previous steps. Kind of forever.
Yeah, I think in practice, you know, I mean, we had the presentation about Minimit, which, you know, I think it's a fantastic protocol, but the notion that we would want to make progress and keep producing blocks indefinitely without having achieved finalization at any time, you know, that I don't think that's a very practical notion. I think in practice, what you want is you want consensus to, you know, jump ahead as quickly as possible, but then you want to have some mechanism to ensure that this gap between where you currently are and what the last thing that you finalize, that gap is bounded. Because if it's not bounded, then the memory consumption will also not be bounded, right? So I think in practice, you always want to have some measure that slows down consensus if it goes too quickly without finalizing anything.
Beautiful. Nice. Yeah, I like that a lot, actually. Okay, so let's come back quickly to this. So to recap, I guess, with all of this detour, if you guys remember, we just had this table, and then you can kind of ask for weaker liveness guarantees. That's another thing that you can ask, and then in this case, you get these broadcast primitives, which are solved with this kind of very simple mental model, which is simple again in theory. In practice, it's another thing. So then what we realize, or at least what I realized reading these things, is asymmetric crypto gives you, what does it give you? It gives you two things. So in the cache notes, that's something that they often have. So you can compare he compares the echo broadcast to the authenticated broadcast. And this is always, so all of like Itai Abraham will always speak of, these linear communication complexity things. I mean, Victor Shoup was ranting about these as well at the beginning of this presentation, if I remember correctly. But it's also related to Pipes models. So these are the models where you, instead of doing all-to-all broadcasts, you instead kind of send all your messages through the leader and then back out. These again kind of rely on having these asymmetric crypto, because you need these certs, which you can only build if you have asymmetric crypto. That's one of the things you can do with asymmetric crypto, and the other one is these transferable certs. So it's just basically the same thing. I mean, it's pretty much the same thing actually. It's just you can build a cert, and then this is kind of what allows you also to compare to go from the Brakas, right? So if you remember the Brakas implementation here for reliable broadcast, which needed 3 separate kind of rounds, you can compress those. You can compress those into a single quote unquote single in a theoretical model round. So these are kind of the two things you can do, right? Either you lower your communication complexity with these certs, or you can kind of because you have these provable certs, you can also sometimes just reduce your number of rounds. So let's come back to this. I think, Jungwei, this is related to what you've been asking, but just to go back to this. So I've been drawing this. I still don't fully know if it's accurate. I haven't gotten like a lot of feedback, but I think that's something that I've been trying to draw. So the idea is you have your spec, right? This is kind of the theoretical world. So you have the best effort broadcast. And then if you ask a bit more, best effort is just like the leader sending and not doing anything. There's no quorum basically. So this is just like, it just means like multicast on the network and then forget about it. If you ask a bit more, so you ask for a quorum, then you get your consistent broadcast. And then if you ask people to rebroadcast the cert after they commit, you get reliable broadcast. And then, so here in the actual implementation world, right, this is kind of what I've just been discussing. So what the Christian Cachin's paper is doing is really just like outlining these different protocols, ones that have PKI assumptions, some that don't, with the odd channels. So anyways, I thought he could have done a better job kind of, showing the full picture. I feel like he kind of started and shows 3 protocols and he's just like, okay, that's it. I don't know. I personally find it a bit kind of insufficient. But the nice thing with this is, so there's this other nice post in decentralized thought called provable broadcast. All right, and then this is just what I've been talking about, is if you're in this PKI model with where you can build certs, then he's kind of there, him and Alexander Spiegelman, which is the guy behind like Narwhal, they kind of rebuild this hierarchy of locked broadcast. Is basically how many rounds of provable broadcast, so how many quorums on top of quorums are you building, and what properties do you get? So it's a hierarchy of what more do you get. And right, so all he's saying is, so you can do provable broadcast, which is just here, like a sender goes to everyone, and then you build the cert. Again, you could also kind of, sorry, so what I mean is, so here when you go to lock broadcast, you just do this twice. Again, this is kind of doing the linear communication trick of going through the leader again, but you could also just compress that into a 2-round thing, which is what we're doing by just having everyone all-to-all broadcast. But I think they just made it this way for simplicity. So this is kind of the outline that I have here on the right. So you can kind of go like this and then build. And then what I like about that post is that he just, they basically examine which protocols that we're familiar with use these kinds of broadcasts. So I think this is going towards the line of like, okay, now we have these broadcast primitives. We can actually chain them, and then they give you kind of nice properties. And then how do you actually put consensus on top to actually get your, in the total ordering kind of FLP theory? This is where you want the total order broadcast, the SMR, or whatever you call it, consensus. So for example, Narwhal and Tusk, you just kind of use this robust lock broadcast, and then you use kind of a, is it timeout? I guess it is, right? Okay, yeah. So I think the first one, so all you need is DAG, or this is the Narwhal and what was it? I think I might be mixing them. This might be Bull Shark and not Tusk. I forget which one is async and which one is partial sync. But one of them basically you just kind of use with one of them just uses randomization, the other one uses timeout, and then one uses so Honey Badger, I don't know if you guys are familiar with this. I think it was the first one, the first protocol in the, so if I go back here. Okay, so this is kind of I think this section is going beyond the reading material for sure, but I think it was just kind of an outline for where we can go next, right? So once you have these broadcasts, now what you're missing from these broadcast primitive is really you want to make sure that everyone terminates. And so how do you get that? And these are kind of in the different models, sync, p-sync, async, right? How do you make sure that that you always terminate? So in the p-sync model, partial synchronous, it's always kind of you have these you just use a timeout and you swap the leader out if the leader, right? So the only condition, if you remember, that we're missing liveness in is when the leader is dishonest, and we're not sure that everyone's going to terminate. So basically you just swap your leader, and you expect kind of that you'll be able to eventually, once the network comes back to the synchronous period, then you'll know that everyone will kind of eventually be in the same round at the same time. We'll be able to make progress and get liveness. In the async models, you cannot do that. So that's why you have kind of a bit weirder constructions. But basically, all of these models are kind of always, in the async model at least, as far as I understand it, everyone always broadcasts. It's not, you never have kind of a single leader. So that's why you build these DAGs, or you build this autobahn like Struck, or in the Honey Badger, it's just everyone synchronously kind of, well, not synchronously, but at the same time, broadcast their changes, and then we run an async consensus protocol on top of the results. in order to kind of decide what goes into, and this is what this ACS property is I forget what it's called, a common subset or something, asynchronous common subset or something like that. So, okay, I think I want to leave it at that. Maybe this was going a bit too far, and oh, this is just the provability. But so I think what I would propose, or if you guys are interested, is the missing link then is kind of maybe going through one of these. And I think this blog post here, the key principles underlying partial synchrony, I think this is kind of a really, really nice post, because it basically does what I've been trying to do. I mean, I got my thinking from this blog post. Basically, you start with a reliable broadcast, you're missing liveness. So then the question is, what do you do to actually get the full termination? And then they kind of outline these, the lock commit paradigm is the one used by everything that is not simplex, basically. So the PBFT, the Tendermint, the hot stuff. And so then they kind of lay this down, and then in the next post, I think here they walk through PBFT through this provable broadcast lens. So I think it's quite nice. Yeah, I don't know. We have maybe 5 more questions if you guys have questions, or if any of this made sense. Yeah. Yeah.
Yeah, I think you discussed view changes, right? At least in partial synchrony and I think in the asynchronous model. In say if we take something like a PBFT, right? So at least for view change, the penalty, at least, I mean, if like a leader fails or is like dishonest, it's I think complexity is like O of n cube, something like that. For it to continue, I guess, and then something like async tag, like a narwhal, or I mean similar, it'll just continue, right? There's no penalty as such for broadcast for it to continue, or like, I mean, is that understanding correct? Or?
Yeah, that's a good question. That is actually, right now it's a bit beyond my pay grade. I haven't like fully integrated all of these models in the blog post that I was talking about. Because yeah, so what I have in mind is basically the simplest thing that you can do is where's the agreement one? I think this one. Right, so the simplest thing that you can do is just have this kind of mental model. So you have a mental model where everyone one person broadcasts, and then we run kind of an agreement on this, and we output. And what you can do also is just I don't know if he does it here. Oh yeah, or the other way here. But yeah, so this or everyone broadcasts, and then we kind of come to agreement. So that's one, right? The question, sorry, that I'm trying to get at is, how do you compose these broadcasts with these agreement boxes? And the point is, this is the simplest model, so you'll see this often. But the problem is, by keeping the broadcast and the agreement kind of completely separate, which is what the Honey Badger protocol does, you have extra liveness. You have extra latency, right? Because you're kind of paying the broadcast latency and then the agreement completely separate. So what actually happens is in all, as far as my current understanding goes, in all of these partial synchronous models, you kind of, they kind of, you cut them in a bit like this. You kind of make them interlock. And so there's no, if you ask like, oh, where is the consensus running in simplex, or where's consensus running in PBFT or Tendermint, there's no such thing, right? So that's why you kind of, you have to reason through them separately. Now, what you're asking is, that's in the good case. In the bad case, when there's a leader that actually faults, and then we need to swap him out, what you're asking is, then you have an actual view change. In that view change, which is, yeah, the ON cube or whatnot, is that consensus? And that, the way I think about it, I do think of that as a black box kind of consensus box, where you kind of agree on the next leader, right? So we want to all agree on the next leader. I don't think that's I think like if Kartik or someone was here, I think they would explain it differently. Because again, I think there's always kind of a quorum game, right? You can just swap the leader as long as you have like kind of quorum intersection, which is what the locking paradigm is doing, right? It's just making that anyone who has locked its value will in the next round kind of protect that value. That's kind of what's happening. So I think that, yeah.
So the mental model here, at least for like just classical BFT style protocols, which is like BFT simplex, all of that is just there's no notion of broadcast and then agreement or ordering, or I mean whatever you want to call it. There's no like clear separation between the two, right? Like I think in Narwhal it's always Narwhal plus task or Narwhal plus something else, right? So I think there's like this clear boundary between the broadcast and then I guess like ordering or like consensus on top, right? Which doesn't exist, I guess, in BFT or in that world. So,
in the partial sync, right? But so that's actually a great example. So that's also why I have the DAG here, right? So the DAG, the nice thing, if you go back to Sasha's post, he says basically in the async model, where I think it's Narwhal and Tusk. I forget which one of Tusk and Bullshark is the partial synchronous versus the asynchronous. But basically the asynchronous one is we just kind of run these rounds of reliable broadcasts. So they're not running consistent broadcasts, they're literally running reliable broadcasts. And then once we have this DAG built, we know that we all have the same DAG. So we can come to basically now what you need is you just need a random coin to decide who's the leader. And we anchor that, basically that determines all of its past like kind of causal DAG history is the thing that's getting committed. Right. So this is going back basically to this, okay, I have FLP, so I need something like consensus to get out of it. What do I do in these models? I just use a random coin to elect the leader. That's all I'm doing. So again, it's not there's no like clear consensus round, right? In that case, literally, you don't even need consensus in some sense. You've just already you've purely used broadcast in a way that is so strong that we all know we have the same local DAG, or at least it's got like these quorum intersection properties. So once we elect the leader, we know that we all kind of reach the same, we will commit to the exact same transactions. I mean, modulo a deterministic function that will reorder this whole DAG, right? In the same way in the execution layer.
Well, but why is still notion then of like broadcast versus like consensus on top, even like DAG style protocols? So if you're saying that broadcast is so strong that we still everyone has a notion of the DAG that's been built. Like how do you?
Thanks, Tobias. Well, yeah, I mean, the way I think about it, but I wish, I mean, maybe one day we can have Sasha come and explain it. So I think I'm not lying, but I might be missing some points. But the way I think about it is, at least, is this kind of this model here, right? Where you take a broadcast and a binary consensus. This is very kind of, again, it's your basic theoretical model that you should think about. But most of the efficient kind of constructions that we make are not like that. They get consensus more kind of implicitly via some other construction. And the DAG works like this. And then I actually don't know how out-of-band works. Maybe out-of-band is one of those where they take a cut. Maybe that cut is actually done via some kind of consensus protocol. I'm not actually sure. Yeah. But it's possible also that in the partial sync world, so when you go to Narwhal, this one, it's possible that in this case, you actually have a real consensus protocol that you're running. Because I do remember, right? I think that's probably what you're thinking of or referring to in the paper. They've actually tested like just Narwhal plus even, I think they had Narwhal plus hot stuff, right? Or yeah, so that is actually a good question. Maybe we can take it offline and ask. Okay, awesome. I think we're out of time. I don't know if anyone has like last minute questions. No. Perfect. Well, anyways, thanks a lot, everyone, for joining. I hope this was useful. It was quite fun for me to present. So thanks, everyone, for being here. And cheers.
Thank you, Sam.
Thank you.